All right, today we're going to review real-time operating systems and try to understand why we use them and some of the key fundamental concepts associated with real-time operating systems. So in the embedded world, we normally have a bit of a unique situation in that we have a system that's going to run for a very long time, and it's going to want to handle a set of activities, but these activities aren't going to want to always be running, but we'll only want to run occasionally when they're ready. So for example, we might have some measurements that might occasionally want to run. We might have an interrupt that might occur when a condition happens, and in each of these cases we want the system to be able to handle and do that task or that assignment. So there is a very simple way to do that, and that's to use a while forever loop. So our code might look like this. We're going to create a couple of flags that'll tell us when our task is ready to go. And then we're going to create a couple of functions, task 1 and task 2. Those functions actually process the data associated with those tasks. And then we'll do a while forever loop, and we'll simply check, is the task ready to go? If it is, we're going to do that task. If it's not, we're going to go to the next task, and so on. Now you can see from this code, there's no real way for the task, that task 1, to become true in this code. So how do we do that normally in the real world? Well, we normally associate each of these tasks with an interrupt service routine. So normally an interrupt will occur from the outside that'll indicate when that task is ready to be run, and then we'll have a function that will set that flag equal to true. We call that function an interrupt service routine, or an ISR. And in order for it to be run, we have to add that function to the interrupt vector table. Now the interrupt vector table is just a table of tasks and their associated interrupts, or ISRs and their associated interrupts. So we have to keep that interrupt vector table updated, and for example, in the Arduino, we run a function called attach interrupt. And what that function does is adds that ISR, that function, as an interrupt service routine and associates with a very specific hardware interrupt. So for example, attach interrupt 2, task 1 underscore interrupt, rising, will add the interrupt vector table to the interrupt vector table at the second location, the task 1 interrupt, in a rising manner. So when the interrupt occurs with a rising trigger, the task 1 interrupt function will be run. Now we need to think a little bit for a moment about function pointers and make sure we understand those. And pointers again are just addresses, if you remember that from CS 124. So in this case, task 1 interrupt is a pointer to the very first machine code location that occurs in our task 1 interrupt function. So it's called a function pointer. It points again to that very first location. So attach interrupt 2, task 1 underscore interrupt rising then takes that task 1 interrupt pointer where it's pointing to in memory and puts it in the interrupt vector table. So when that interrupt occurs, the system will know to go to that location and execute that function. So here's an example what our interrupt vector table might look like after we run the attach interrupt function the way it's defined here. So we haven't defined interrupt 1 or interrupt 3, but interrupt 2 is defined, and it's connected to the task 1 interrupt function. So we know that when that interrupt occurs, we're going to go out and execute that function in memory. Now this kind of system works very well, and we use it for a lot of applications. The challenge is if we're going to constantly be using the processor and its capabilities simply to check to see if each task is ready. And the other challenge is if we have a lot of tasks and we're at the upper end of the tasks and checking them, and the bottom end of the tasks get their flag set, we won't get to them until we get to them in the loop. So there's no way to, if something happens that we want to respond to urgently, to make sure that happens right away. So as a system, we decided to come up with a solution by implementing a real-time operating system. So in a real-time operating system, we define tasks. Tasks are really associated with running a certain function or a set of code. And what we do is introduce the idea of a scheduler. And a scheduler is going to allow us to decide which of all the tasks that we have waiting out there should be running. Now, in addition to be able to check and see which tasks should be running, we're also going to want to be able to tell which tasks shouldn't be run. That is, those tasks that are still waiting for a condition or waiting for an event to occur. When a task is waiting for an event to occur, we're going to call that a blocked task, or a task that shouldn't be run. So our RTOS is going to contain code and data. It's truly an object, and it's going to contain code and data to create tasks, to block and unblock tasks, and to schedule tasks. So again, what we have over on the left-hand side are a set of tasks. These are things that we're going to want to do when the condition has been met. On the right is our ISRs. That's going to register when an event has occurred that will allow one of our tasks to run, and our RTOS is going to efficiently and effectively handle all of that. Now, at the heart of our RTOS is a scheduler. And at the heart of our scheduler are two queues and some very efficient code. Now, if you'll remember what a queue is simply an array of elements of a certain kind. And in this case, we're going to have two arrays, and each of the elements of these queues, or these arrays, are going to be a process or a task. Right? So we're going to have a ready queue. That's a list of tasks or processes or threads that could run based on their priority. We're also going to have a queue of tasks. These tasks are going to be blocked. That is, they're going to be a set of tasks that aren't ready to run. They don't want to run now. We're going to wait for their condition to be met. And then our scheduler is going to be a set of code that we're going to run periodically. And every certain time, we're going to go to try to find out which task should be running on the processor. So let's just walk through a very specific example to see. So when we hit the button and reset our processor, the processor is going to go to some address. Normally it's 00000, and it's going to start running either the BIOS, or sometimes we call it the board support package, the BSP. And this is a very simple set of commands that's going to establish where our memory is, where our hardware is for communication. It's going to initialize all of our variables. It's going to set up our interrupt vector table and all the addresses for our I/O. Once we've set up all of those BIOS variables, all the hardware is now configured, we're going to go to main. And one of the very first commands that is going to be in main is the init RTOS. And init RTOS is going to set up our block queue. It's going to set up our ready queue. It's going to establish all of the data structures we need for our scheduler. Now notice there's nothing in the ready queue, there's nothing in the block queue at this point, but the data structures have been established. Now we're going to create a task. We're going to call a function called create task. Notice this is all still be running inside of main with a single thread of execution. And in this case, we're going to create task simply adds this task to the ready queue. So the task has been added with a priority and with the function that we want to run when we first run the task. So the task1 function is a function pointer. Notice that task1 function exists over in memory. That has been created by our compiler. It's out in our program memory, and it's ready to be run. And now we've, in our ready queue, set up an element that says for task1, when you very first run that task, go to the very first location in the task1 function. We're going to do the same thing in task2. Oh, I should also point out, by the way, notice that over in our heap memory, we have also established a few variables that we're going to need later, because we're going to be moving from different tasks. And a key element of this, of course, is that each task has its own program counter, its own stack, its own call stack, and its own register states. So each time we determine that we're going to switch which task is running on the processor, we're going to have to save those three specific items. And when we want to recall and run a new task, we're going to have to recall those items. So for each task, notice we set up a register state location in memory to store those, and a stack location to store those. And there's also a location that we're going to have in heap memory that'll store the program counter for each one of those. So now we have two functions on the ready queue with their priority. And now we're going to call start RTOS. And start RTOS is going to run our scheduler. So our scheduler is going to store the current context. That's going to look at, well, what's currently be running on our processor. Let's make sure we store that. And in this case, because nothing is there, we don't have to store anything. And then we go to the ready queue evaluation. Now what we're going to do is walk through each element of the ready queue to try to determine which task has the highest priority. And in this particular case, we're going to say the lower the priority, the higher the priority set. So number 1 is going to be high priority, 2 is going to be slightly lower priority. So in this case, we're going to determine that the task1 function should be run. We want task1 to run because it has a higher priority. So we have to restore the task state, and then we're going to go to task1 function, and notice we're going to go to the very first memory location as defined by our ready queue, which is the task1 function, and it's now got the processor. It's going to start running. So we're going to start going through its function. We're going to go to while 1, which is a while forever loop. We might get a value, which is great. Then we're going to hit vtask delay. By the way, notice that the task1 stack at this point has task1 function and get value as function calls. Then we're going to go to vtask delay. That is a function that's in our real-time operating system, and in this case what we're telling the system is we want to stop this task for 100 milliseconds. We want to have this task not run for 100 milliseconds. So we're going to set a delay variable associated with the task to be 100. Now because we don't want the task to run right now, we're going to move it to the block queue. Notice that it's not in the ready queue anymore, it's in the block queue. And now we're going to start doing nothing really, because our task doesn't want to do anything. It wants to be blocked, it wants to wait. Now at some point our timer interrupt occurs, and this timer interrupt will be associated with how often we want our scheduler to run. So periodically, we call it a time slice, we're going to interrupt with a watchdog timer, and we're going to say run the scheduler. And so this timer interrupt has occurred. We're going to go to the timer interrupt ISP, and we are going to run our scheduler. Now what does our scheduler do? Well, the first thing it's going to do is store the current context, and our current context is associated with the task 1. So we're going to store the task 1, the register states in our processor to the task 1 register state memory locations in heap memory. We're going to store our task 1 stack. Then we're going to look at our timer variables. That is, all of the tasks that said we wanted to sleep for a certain specific time, we're going to update them and check to see if the timer variables have expired. In this case, they haven't for task 1. We haven't waited long enough. We just got placed on the queue. So now when we go to the ready queue evaluation, there's only one task, and that's the task 2 function. So we're going to restore its register states and its stack. The stack pointer is going to point to the task 2 stack now. And sure enough, we're going to start running the task 2 function, because that's the function, that's the task that's ready to run. And we're going to, because it's the first time we've run it, we're going to start right at the start of the task 2 function. Now we're going to again run that, and sure enough, we got a while forever loop. And in this case, we're just going to get a value, and each time we run it, and we're going to do that for a certain length of time, and then our watchdog timer is going to interrupt us again. It's going to say, now it's time to run that scheduler. Let's see who's up. Okay, let's go run the scheduler. We store our current context, which is the task 2. So we're going to store its stack pointer, and we're going to store its task 2 register states, and we're going to store its program counter. We're going to update the timer variables. We're going to look to see, is there anybody waiting over in the block queue for a certain time? In this case, we're going to assume that we haven't waited long enough. So we're going to leave task 1 in the block queue. It's not waited long enough yet. Now we go back to the ready queue. What's there? Only task 2. We're going to restore its state. So we're going to bring back its register states to the processor. We're going to restore the stack pointer to the task 2 stack. And notice that we're going to go back exactly where we left off in task 2. We don't start from the start, but rather we are going to go back to the last, right after the last command we executed when we got interrupted by our timer interrupt. We're going to go ahead and go and just keep going on task 2, getting a value, and then our timer interrupt is going to hit us again. That's going to tell us to go ahead and run our scheduler. We're going to store our context, which is task 2 stack and task 2 register states. We're going to update the timer variable. Now let's assume at this time that we have actually gone past our 100 millisecond delay. Let's assume this time that the scheduler looks at those variables and says, yeah, we have waited over 100 milliseconds. So what we're going to do is we're going to move that task 1 function from the block queue to the ready queue. So because it's waited long enough, it's sat in the block queue longer than our 100 milliseconds, it's now been placed back in the ready queue, and we go through a ready queue evaluation. Which of those functions is higher priority? Which one should be running? And in this case, because the lower number is the higher priority, we're going to go ahead and run and say, oh, now it's time to run task 1 function. So we're going to restore the task 1 register states and the task 1 stack, because we want to run that function now. And we're going to go ahead and run the task 1 function. Notice we're not going to start at the start of task 1 function. Rather, we're going to go to the location of the next instruction right after vtask delay. In this case, it's our while loop. So that's where we left the function. That's where we're going to go back in. And we're going to hit and get the value, and then we're going to hit vtask delay. So, in summary, in a real-time operating system, our key functionality is a scheduler. The scheduler has 2 very specific data structures that are important: the ready queue and the block queue. The ready queue is an array that holds a set of tasks or processes or threads that are ready to run. The block queue holds a set or an array of tasks, threads, or processes that are not ready to run, that are waiting for some event or some amount of time for them to be ready to run. The scheduler is run based on our watchdog timer interrupt. It interrupts it at very specific times. Each time it interrupts us, the scheduler runs. It first stores the context, which is the register state, the stack pointer, and the program counter. It updates any timer variables. It then looks at the ready queue to decide which task should now be running on the processor. Once that's determined, it restores that task state, which is the register set, the stack pointer, and the program counter, and then that task begins to run. And it'll run again until the next watchdog timer interrupt. So hopefully that's been a good review of the scheduler and real-time operating systems. Next time we'll talk a little bit more about how to use semaphores to do some synchronization with tasks.